call on this computer? Is it recording? Okay, it's recording. Oops, sorry. For people that are not here, you just have to work out the first two questions on your own. I'll post the solutions as well, so don't worry about this. All right, question 3. You have a 2-to-2 process. So you have like a particle 1, particle 2 coming together, and then out comes particle 3 and particle 4. So whatever happens in here is a black box for now. Don't worry about it. And the Mandelstam variables, which relates the form momentum of these particles. So S is the incoming particles, sum of their form momentum, and T is the one incoming, one outgoing, and U is the other one incoming with the other outgoing. So we have to show this relationship. This is just algebra. There's absolutely nothing to it. You just have to plug these into the left-hand side and see what happens. So S plus T plus U will just be this one squared. So P1 squared plus 2 P1 mu P2 mu. So remember, if there's no Lorentz indices and I say squared, explicitly you have to write this like kind of repeated index to show that you're summing over them to take the inner product. But if it's just by itself, you can just put the square, and that's implicitly telling people that it's an inner product. So P2 squared. And then T is plus P1 squared minus 2 P1 mu P3 mu plus P3 squared. And then last one is U plus P1 squared minus 2 P1 mu P4 mu plus P4 squared. Okay. With form momentum, if you have P mu and then dotted with the self, so the square of it equals P squared, this is always equal to M squared, mass of the particle. So this is a Lorentz invariant relation. So kind of not a theorem exactly, but it's like kind of, it always equals to mass squared. So we can just replace all of these square terms with a self with just the mass. So that's equals 1 P1 squared, 2 P1 squared, 3 P1 squared. So that's 3 times M1 squared, and then 1 for each of the other ones, plus M2 squared, plus M3 squared, plus M4 squared. And we just have to deal with all these other inner products, P1 mu. I can factor it out. So I get P2 mu minus P3 mu minus P4 mu. Okay. So yeah, you're gonna have to either expand out these inner products individually, in which case I'll just do one for example. So if you have P1 mu into inner product with P2 mu, then what happens is that you get the energy of 1, energy of 2, minus the spatial part gets a minus because we're still sticking with this signature, minus the 3 vector P1 multiplied by 3 vector P2. And this is the same for all the other ones. Okay, so I'm just gonna rub this out. But rather than doing it individually, then we just look at this bracket right now and say, okay, 3 momentum and energy are both conserved individually. And since 4 momentum is just made up of the energy and the 3 momentum, then they're both individually conserved, then 4 momentum must also be conserved. So the 4 momentum conservation in this case is P1 mu plus P2 mu is equal to P3 mu plus P4 mu. So if I just take these to the other side and I see that P2 mu minus P3 mu minus P4 mu is equal to minus P1 mu, just from conservation. So I'll just plug this back in here instead. So this is equal to 3m1 squared plus m2 squared plus m3 squared plus m4 squared minus 2 P1 mu P1 mu. Oh, sorry, it's an upper index version because these are all upper index. And this is just P squared. So this is just equal to minus 2 m1 squared. And that minus that, so then we only have one left. So m1 squared plus m2 squared plus m3 squared plus m4 squared. So yeah, the only trick is knowing that the p squared is equal to m squared, and then using form momentum conservation to simplify this term. You could have, if you expanded out each inner product individually and then use the energy and 3 momentum conservation individually, you will also arrive at the same answer. So like if time's not an issue, then either way will work. But in an exam, if you're like restricted for time, then remember to use full momentum conservation. It works exactly the same way. Okay, any questions? No, this one should be pretty easy. This is just algebra. Okay, question 4. Show that the gamma to positron plus electron interaction cannot occur in a vacuum. So what this is saying that you have a light coming along, a photon, and then it suddenly spontaneously turns into an electron and a positron. This can't happen if heuristically it's just a momentum conservation issue. So this photon would come in with some forward momentum p, like p gamma, coming this way. By momentum conservation, the electron and positron pair has to end up with p gamma amount coming out into the forward direction as well to just conserve momentum, and you have to conserve momentum. But the problem is that for momentum, part of it is energy, and some of this photon energy has to be put into creating the mass for the electron and the positron. So if you have mass that use up some of the momentum, then you obviously don't have enough left over to conserve momentum. So that's like the hand-waving way of saying why this can't happen, because you don't have enough momentum to conserve itself and also create the mass. But rigorously, you can show it quite easily. So again, use full momentum conservation. So I'm saying that if this happens, then the full momentum of the photon, p gamma, has to be equal to the full momentum of the electron plus the full momentum of the positron. This has to hold. Okay, equivalently, the square also has to hold. So now I could just square both sides. And okay, the left-hand side, p squared, is just m squared. So in this case, let's pretend that we don't know photon's massless yet. So I just say m gamma squared. And for the right-hand side, this could get complicated, but we can choose a particular reference frame to work in. And because Lorentz invariance tells us that if something physical happens in one frame, it has to happen in every single frame. So we can choose the most convenient frame to work in and then extrapolate that result by transforming later. So in this case, this has to hold in every frame. And one of those frames is the center of mass frame of the electron positron. So in the center of mass frame, I know the electron positron just flies off in opposite directions, and they all have 3 momentum that's opposite each other. So this is minus p. So since the 3 momentums are opposite each other, when you add them together, the 3 momentum part cancel out. So you end up with just the energy. So you end up with just E, energy of the electron, plus the energy of the positron squared and in center mass, because the momentums are opposite. And energy you can equivalently write as m electron positron have the same mass. So I'm just going to write as me gamma plus me gamma squared. And so these two are the same. So it'll just be 4 me squared gamma squared. And now we go back and say, okay, a photon's massless, so this has to equal 0. And okay, electron can't travel at the speed of light, so gamma can't be 0. Gamma has to be a finite number. And the mass of electron we know is a finite number. So this relation makes no sense. So this is a contradiction. So that's why it can't occur in a vacuum. You need something else to provide like a recoil to supply the additional bit of momentum to give this enough rest mass. Otherwise, just with the incoming photons momentum, you don't have enough energy to go around for everybody. So contradiction can't happen. Yeah, so normally with these kind of pair production mechanisms, you will have the photon hit a nuclei or something that's heavy. And the nuclei, because it's so heavy, it doesn't recoil at all. So you have no like visible effects, but it's got enough momentum to elastic collision to give it some momentum to make up the gap that you need to create the rest masses.
Why does not being in a vacuum help?
It just because you have to hit something. So in a vacuum, you can't hit anything. So that's the only.
Okay, so we need like an extra thing in this process to enable it, some kind of catalyst.
Yeah, you need another particle in there for the photon to kind of hit and then create these two. Yeah. So yeah, the vacuum statement really is just saying that you don't have any options. You don't have something else in there for you to interact with.
I was just thinking about because the way I understood this is it's because the photon in a vacuum is traveling at the speed of light, therefore it's fully time dilated, so it has no time to do anything.
No, you got to think about more along the momentum conservation. So the photon's momentum, form momentum has to be conserved, but then you need some of this form momentum to create the rest mass of the electrons. And then what's left over is obviously not going to be enough for you to say that it's conserved.
So you're saying this is a different concept to, what's that, is it muons or something? Yeah, it's a different concept.
Different altogether, yeah.
Okay.
Okay, if no questions, anybody else? All good. Okay. Then let's do question 5. So question 5, we have a decay, so 1 to 2 process. And then we want to show that the mass of the decaying particle can be related to decay daughter particles by this relation. So, okay, they wrote down C in here, but I'm going to work in natural units. So I'm just going to call C equals 1. Again, okay, so pictorially, this is a particle A coming in, and then it decays into 2 daughters called 1 and 2. And between these 2 momenta, you have an angle theta. Okay. In this case, we again start with form momentum conservation. So PA of mu is equal to P1 of mu plus P2 of mu. I realize I've been mixing these up and low. So in this case, I start with the lower. In this case, I start with the upper. Don't worry, don't stress about it. It makes 0 difference in flat spacetime. In curved spacetime, you have to, there's some distinction, but in Minkowski metric, doesn't really matter. You can start with the upper or lower, it's the same thing. Okay, and again, we want to square both sides. So PA squared is equal to P1 plus P2 squared. I dropped the indices, but these are still 4 vectors. Okay, so left-hand side is just, again, MA squared with the form momentum relation. And on the right-hand side, we get M1 squared from the P1 squared term and M2 squared from the P2 squared term. And then we have to do an inner product by hand, P1 mu, P2 mu. Okay, but we know the inner product is just the energy part and the momentum part done separately. So 2 times E1, E2 minus P1 vector dot P2. Okay, and then I take out factor of E1, E2 at the front. So I get M1 squared plus M2 squared plus 2 E1, E2, 1 minus P1 dot P2 over E1, E2. Okay, now let's just look at this term, this P1 dot P2 divided by E1, E2. That's the only thing we have to massage. The rest of it is all there. We got the energy, we got the masses. So P1 dot P2, as we see, the 3 momentum here are just 2 vectors that have the angle theta between them. So P1 dot P2 is just P2. It's just equal to the magnitude of P1, magnitude of P2 times cos theta. So this term, it just becomes 1 minus P1 on E1, P2 on E2 times cos theta, the angle between them. And everything else is the same. Okay, now this P1 divided by E1, if you just go back to the definition of relativistic momentum, 3 momentum, and relativistic energy, and we see that 3 momentum relativistically is equal to mv gamma. So it's just the normal non-relativistic momentum with a Lorentz factor tagged at the end. And the energy is mc gamma. Oh, sorry, not since c equals 1, so I'm just going to m gamma. But normally it'll be mc gamma. Right. So then P1 divided by E1 would just be, move over a bit, equal to m1 v1 gamma divided by m1 gamma. All of these cancel out, so I just end up with v1. And same for P2 on E2. So it's just equal to the velocity. So it's kind of weird that you think that, like, in non-relativistic mechanics, the momentum divided by the mass gives you the velocity. But you just got to think, because energy and mass has this correspondence in relativity. So then rather than dividing by mass, you're dividing by energy, it gives you the velocity. But this is essentially just a relativistic version of this classical mechanics relation. But okay, so now we have m1 squared plus m2 squared plus 2 e1 e2, and then 1 minus v1 v2 cos theta. We start off in natural units, so we don't have the c's, so let's put it back. It's not that hard. You just have to put one c down here and one c down here. How do I know just one? Because if you look at this, everything in this bracket, this term is just a 1, so it's dimensionless. So then this term has to be also dimensionless. You can't add or subtract two terms that have different units. So cos theta have no units if theta is in radians, so this is dimensionless. So the only thing I need to get rid of the velocity dimension is just dividing by one factor of speed of light, which is also velocity. So now everything in here is dimensionless and everything works out. And you can call these rapidity factors, beta 1 and beta 2. Yeah, and that's it. That's the answer.
So does this equation work in any reference frame? Because quite a lot of the terms in it like are dependent on reference frame, but I guess the
Sorry, can you? You're really quiet. Can you say that louder?
sorry. Like, does this equation depend on which reference frame you're in? Because a lot of the terms like energy and theta and stuff would depend on which reference frame you are, but do all the differences cancel out?
Yeah, so this one is, it doesn't depend on reference frame. So if you switch frames, then these energy and these velocity terms and this angle, they will change accordingly. So you can transform between frames, but this one is independent of what frame you're in.
Okay, thank you.
Yeah. So the way you know that this is independent is because both left and right hand side has to transform the same way. And if you look at the left hand side, you have the rest mass, and the p squared equals m. This relation is called a Lorentz invariant quantity. So this quantity doesn't transform when you go from frame to frame. So that means whatever happening on the right-hand side has to kind of sort itself out internally if you have any frame transformations, because you can't cause anything to happen on the left-hand side. This is why this starting with four momentum and squaring them is such a good starting point, because it is you don't have to think about what frame you're in. You can, but you don't have to.
Do you have any tricks for converting from natural units back to SI if we get lazy and then decide not to be lazy later?
There is no tricks. You just have to think about it. So if you everything in natural units is in energy. And then you just have to think, okay, energy in SI is kilograms, what was it, meters square per second squared. And now if I want to transform this back into whatever SI units it was, so let's say mass is given in like electron volts, so it's energy in natural units, but I want to get it back to kilograms. So I look at this and say, okay, they differ by these two factors, and then I have to divide by two powers of velocity. So that means c squared. That gets you back from energy back to kilograms.
Okay.
Yeah. So you just have to start here and then put in c, h bar, and kb until the units work itself out.
Okay.
No, there's no shortcuts, I'm afraid. Or you actually, I just look up a table. If you ask me to do it on the spot, I probably can't do it. Okay. Question 6. Find the maximum opening angle between the photons produced in the decay neutral pion to gamma gamma, if the energy of the neutral pion is 10 GeV and given that the mass is 135 MeV. Okay, so this is a 1 to 2 decay. So let's call pi A and the photons 1 and 2. Then it's just this question. So we can just use the answers here as a starting point for question 6. So we know that MA square has to be M1 plus M2, blah, blah, blah. So then if A is pion, then that means M pi squared is equal to, okay, M1, M2 are the photon masses, so they disappear, they're 0. So all we have left is 2 times the energy of photon 1 times the energy of photon 2, and then 1 minus V1, V2 cos theta. I've gone back to natural units again. So that's our starting point. And now we look at the, okay, and also because in natural units, V1 equals v2 is equal to speed of light because they're photons, and because in natural units is equal to 1. So I can even simplify this a bit further. So it's just 1 minus cos theta. Okay, and now I want to sub out one of these energies with energy conservation. So energy conservation tells me the energy of pion has to be equal to the sum of the energy of the photons. And so I can rewrite E2 as E pi minus E1. And putting this back in here, I get 2 times E1 times E pi. Ooh, one too many slashes. E pi minus E1, and then 1 minus cos theta. Okay, and okay, this is a given number. This is the given number. I have one free parameter, which is E, and I want to determine the maximum angle. So I want to rewrite this as a function, as cos theta as the function of energy. So I can work out like at what energy I get the maximum angle. So do a bit of algebra. Hopefully I don't have to go through this step by step. So I'm just going to tell you the answer. 1 minus m pi squared divided by 2 E1 E pi minus E1. Okay, cool. Now we just have to find the maximum angle from this expression. M pi is given, E pi is given, so one parameter. I can't differentiate, so I'm going to use Mathematica. So here we have cos theta is equal to 1 minus m pi squared divided by 2 times E1 times E pi minus E1. Okay, and then now I just want to get the derivative is equal to d of cos theta with respect to the energy of the photon E1. Okay, and then just simplify that. Cool. Okay, now that's the first derivative, and we just set that to 0. So we want to solve for derivative equals 0 for E1. And it tells me the maximum angle happens at when E1 is equal to the energy of the pion divided by 2. So then now I sub in cos theta, and I sub in E1 is equal to E pi divided by 2. Okay, and now I just want to evaluate this. So I get 5 subbing in. The mass of pion was, what was it again in the question? 135 MeV. So I'm just going to work in MeV, so I call it 135. And then energy of the pion is 10 GeV. So converting that to MeV is 10,000 MeV. And give me that as a number. Cool. Okay, so the maximum cos theta is 0.999636. So, but then I want the maximum angle, so I want to invert the cos. 0.999636. So the maximum angle happens at 0.02698 or 0.027, that's called. So that tells me that theta max is equal to 0.027. And it happens at when E1 is equal to E pi divided by 2. So that tells me that the maximum angle happens when the two photons split the pion energy perfectly and they go their separate ways. And that makes sense because if they both have the same energy, then it's symmetric, and then they open up the largest angle between them. Yep, any questions?
If you, so you maximized cos theta.
Yep.
But doesn't that mean that you found like the minimum angle, because like for larger values of theta, cos theta gets smaller?
Good question.
Or I guess you actually just found the derivative of, maybe you actually found like the minimum of cos theta rather than the maximum, because we just set the derivative to 0. Don't actually know if it's a minimum or a maximum. Because that would work if you minimize cos theta, then you're maximizing theta, kind of thing.
Good point. Let's see. Let's look at the second derivative. d of cos theta wait, no, d of the solution, d of the derivative. Oh God, okay, and then 8 sub in E1 divided by 2. Okay, so that'll be negative. So it is a maximum. I don't know. I'll come back. I'm honestly a bit stumped here. That is physically the right answer. So there must be some mathematical thing that's slipping my mind right now about maximizing cos theta gives you a max theta. Yeah, sorry, I can't answer you right now. If I think of it, I'll come back to it next week or something. But physically, I am fairly certain this makes sense as the right correct answer. Like if you look at what's actually happening. Good question. Anything else? All right, let's move on for now. All right, question 7. So the maximum of the pi minus and proton cross section, which occurs at this pion momentum, corresponds to the resonant production of a delta zero baryon. And okay, that tells us that this resonant production is equivalent condition to saying that the mass is equal to the center of mass energy of the incoming two particles that are colliding. So remember that S is equal to P1 plus P2 squared. So in this case is P pi minus plus P proton squared. So it's the center of mass momentum of these two added together. So when these two, when the square root of this is equal to the mass of the particle that you want to produce, you manage to produce them resonantly. And now I want to find what's the mass of m delta. So we're just going to use this relationship since it's given to us, and we're just going to calculate this S, and that should give us the mass. So calculating S is just going to be, okay, E of the energy of the pion plus the mass of the proton, and then, energy of the pion plus the energy of the proton, and then the 3 momentum of the pion minus the 3 momentum minus the 3 momentum of the proton. Okay, and this is squared. Okay, and now again, we can work in any frame that we want. So let's work in the rest frame of the proton. So that means the energy of proton is just equal to its rest mass, and the 3 momentum is equal to 0. And that makes it quite easy. So we now just have E pi plus MP, and then this one is just the pion's momentum and squared. Okay, now if we just expand this dot product, we get E pi plus MP squared minus P pi squared. Okay, because P pi squared, you don't have to worry about an angle, is squared with itself, so it's just the magnitude squared. Now for here, the energy of the pion can be rewritten in a way that we know the energy of any particle is equal to, energy squared is equal to the momentum squared plus the mass squared from the dispersion relation. So the energy is equal to square root of P squared plus M squared. So we're going to use this to put in here. So we get square root of P pi squared plus M pi squared plus MP all squared minus P pi squared. Okay, now we know everything. We know the mass of proton. Okay, it didn't give to us, but you can look this up. You know the mass of proton, you know the mass of pion, and you're given the momentum of the pion is 300 MeV. So then all of these are just numbers you can plug in. And okay, so the numbers you eventually get are the S is equal to 1678900 MeV. And since the mass of the delta baryon is the square root of S, so we take the square root of that. So M delta is equal to root S. So that's just equal to 1295. 1295 MeV. And if you look up the actual mass of delta, like experimentally, this is about 1232 plus or minus 2 MeV. This is a pretty good approximation. I'll probably round it off a couple of significant figures in the mass of the proton. I assume there's 1 GeV or something. But yeah, the answer still gets you pretty much close enough. So yeah, a lot of these, most of these revolve around taking the square of some form momentum, and then you just have to learn to figure out like when to use what tricks. So like subbing in the energy as this form, or subbing in energy as like the M gamma and the P equals MV gamma. These are all equivalent. So like if you sub in the wrong thing, you probably just be getting the exact answer, but taking a bit longer. But overall, yeah, if you've seen them once, then you know which one to sub in, then these things fall out quite easy. Okay, any questions? Okay, if not, then okay, got 5 minutes, so we can go through some of this natural unit stuff. It would be really quick. All right, so natural units are usually given in energy units in EV. Which one is it, GeV, MeV, KeV, is kind of up to you. The only difference is going to be how big this power is going to be. But yeah, in this case, I chose GeV. And then you go C, H bar, and the Boltzmann constant, just trying to put a combination of these back in until you get back to correct SI units. So first one, the mass of an electron. So as I said before, mass is in natural units is in energy, and that's equal to kilogram meter square per second square. And if we want to turn this into just kilograms in SI units, then we have to add in 2 powers of the speed of light, c squared, for the m squared per second square to cancel out. So that means me divided by mass of electron divided by c squared, and is equal to, so in this case, we put in the energy version of it, so 511 keV divided by 3 times 10 to the 8 squared meter square per second squared. Okay, and since they've given us this in GeV, so let's turn this numerator into GeV to make it easier for us. So we get 511 times 10 to the minus 6 GeV divided by 3 times 10 to the 8 squared meter square per second squared. Okay, work out the number. The number turns out to be 9.0958 times 10 to minus 31 kilograms. All right, sorry, I missed one step here. So you technically should have the number divided by the, okay, c squared, I'm just gonna write it back in. And then you're gonna tag on this number to convert the GeV back to joules. So times 1.602 times 10 to the minus 10. And then once you combine these numbers together, the GeVs, kilogram meters per second squared, these cancel out with these, and then you're left with just kilograms. All right, 2, mass of the xenon isotope. So Xe of 132 tells me there are 132 protons and neutrons. Protons and neutrons, they're slightly different in mass, but in the scheme of things in particle physics, they're close enough. They're both approximately 1 GeV. Neutrons slightly heavier, slightly closer to GeV, but protons close enough, so we just call them all 1 GeV. So then the mass of xenon is 132 GeV in natural units. That's why natural units is useful, because you can do dumb shit like this, where you can just sub it in. Okay, question 3. the lifetime of the W bosons approximately in SI units are given. Okay, find the lifetime of W boson in SI units, given that in natural units is this. So tau is equal to 0.5 inverse GeV. And if I want inverse GeV to go back to seconds, then I look back here, it says H bar gives me a GeV and a second. So if I just multiply by H bar, so tau times H bar will give me 0.5 times whatever number H bar was, 6.582 times 10 to the minus 25. And I have the inverse GeV from the tau and then a GeV second from the H bar. The GeV and inverse GeV cancels out. So the rest of it is just seconds. So that gives me about 3.3 times 10 to the minus 25 seconds. With these, you can check like kind of at the end to see if it makes sense. If you got a very large number, it's you're gonna have to go back and check if you got in the right order, because a W boson is meant to be very short-lived. So this being a very small number tells you that you're on the right track. Okay, and last one, a cross section measured in 1 picobarn, where 1 barn is this meter squared, and I want it in natural units. So, okay, now we want to get meters. So here we have H bar C gives me GeV meters. So I can use this to cancel out the meter squared and left with GeV squared, which will give me the natural units. So let's do it here. So 1 picobarn is equal to 1 times 10 to the minus 40 meters squared, because pico is times 10 to the minus 12 and 1 barn times 10 to the minus 28. And then I multiply this by, divide this by H bar squared C squared. Then I get 1 times 10 to the minus 40 divided by 0.197 times 10 to the minus 15 squared. And the meter squared on top, and then GeV squared meter squared at the bottom. So these two cancel out. And I'm left with 2.58 times 10 to the minus 9 inverse GeV squared. And that's picobarn in natural units. So yeah, probably worth to get a printing of this on your wall. And then if you ever need it, you can just go find the units, see what cancels out, and then multiply with these factors. And the unit should work itself out. And then the numerical factor you get out of front is what the value is going to be in that new unit system. Cool, that's it for today. We managed to get everything. Any questions? Okay, if not, if you are thinking about doing honors, do go to the info session. That should be like in 5 minutes. That would be helpful. And otherwise, don't forget you have a quiz due a Friday before 5 p.m. And I would post up the solutions and a recording of this on Moodle, and also post up next week's questions. And if you get a chance, do try the questions before coming to tutorials and let me know which ones you want to go through. Otherwise, thanks for your attention, and I'll see you next week.
Thanks, Joe.
All right.
Thanks. See ya.
Thank you.
See ya.